Hi everyone. Today in our last talk, we are hosting Dr. Anahtarcı, Dr. Berkay Anahtarcı. A little bit, we are very actually honored, like to have him here, like because of the some problems, technical problems of the previous weeks. Like so, he is very kind to accept our offer second time. A little bit background about him. Dr. Berkay Anahtarcı received his bachelor's degree in mathematics from Boğaziçi University, and afterwards his PhD in again mathematics from Sabancı University, which is going to be the like host of our symposium in couple weeks, in 2 weeks. So a little bit advertisement. Since 2015, he has been a faculty member in the Department of Mathematical Engineering at Özyeğin University in Istanbul. And later in 2024, very recently, he received the Faculty Teaching and Learning Excellence Award from Özyeğin University. His research focuses on mean field games and reinforcement learning. Today, he's gonna focus on intersection of reinforcement learning and large language models. I think you can start, Dr. Yeah, Anahtarcı.
Thank you very much for the kind invitation and introduction. So today I will talk about policy optimization for reasoning in large language models. So this is a talk about reinforcement learning, basically, from my point of view. And let me introduce what I will talk about today. So I will first give you the basics of reinforcement learning. And if you know a little bit about reinforcement learning, this is going to be like a refresher. And if you're not, I will go step by step and develop the policy gradient methods, which is the core of the talk. And then I will pass to large language models, give a brief introduction, so to get some idea about these models. And then we will jump to advanced policy optimization. So this is going to be a talk about the TRPO, PPO, GRPO, GSPO. So you see these names, and these are the popular algorithms that are used by ChatGPT, DeepSeek, or Qwen. And GSPO is the recent model. So we postponed this talk, and it's kind of luck because GSPO was introduced like 2 weeks ago. Now I had some chance to read it and include it in the talk. And then I will go to reward modeling from preferences. So this is reinforcement learning from human feedback, and DPO, which is not related to reinforcement learning, but it's a model which is quite new again. So you will learn about how to optimize a policy. So let's first start with the reinforcement learning. Of course, it's going to be a whole semester lecture if we go in details, but I will briefly say what is reinforcement learning. So an agent in an environment learns how to act optimally interacting with an environment. It means there is an agent in an environment and he or she learns by trial and error. So you may think of like riding a bicycle. So you can't learn it from a book. You try, you fall down, and so on. After all, you learn how to ride. So again, this is an example which is not related to large language models, but this works in general. And we can compare reinforcement learning with supervised learning. So this is not a learning from labeled data. It is not the case. And the agent will earn some rewards, which reinforces desirable behaviors, or it's going to be punished, or he or she will be punished if it has some harmful, say, acts. So the agent receives a reward if it acts in a nice way. He or she will be penalized for harmful behaviors. So I will explain what this means in terms of large language models. And the key part is this: there will be a balance between exploration and exploitation. So these are the popular names. And exploration means the agent tries to learn or tries to behave using new action set. Or exploitation means you know how to act in a nice way, so just do it. So you choose the known good actions. This is called exploitation. And if you look for some other actions, this is called exploration. So you need to balance those things, as I will explore. So what is the terminology here? This is the popular terminology, and we should know the basics because I will use it in the future. So an agent interacts with the environment and the actions. So the agent interacts with the environment through actions. It means you take an action. For example, if it's a robot, it turns right, it turns left, or go straight. So this is called AT. It's going to be action. And state gives the description of the environment at that moment. So for example, if you go from one point to another, then this is going to be your new state. Or in terms of large language models, the model predicts the next word. So the whole words that are generated plus the last word is going to be the state, for instance. So it's going to be described by ST. And the idea of reinforcement learning is this: the agent will be penalized or will be rewarded, as we talked about it in the previous slide. But the idea is to maximize the accumulated reward. So we will describe the reward by small rt or lowercase rt, and the return, as I will introduce in the next slide, it's going to be capital RT. So the agent may not act in the best way, for example, in one step, but in the future, in the long run, we expect the agent to behave in such a way that the accumulated reward is maximized. So this is the idea. And the states and actions will be discrete or continuous, but I will talk about the discrete case because this is easier and easy to understand. And here is the chart, which is kind of popular chart. And I used AI to generate all these throughout the lecture. So you will see these charts. So these are all AI generated. Of course, I spent lots of time to do that. But here is the thing. There is an agent. He or she acts. So let's say it acts, and then it changes its state. And at the same time, it is awarded a reward. So you make an action, and then you receive the next state and the reward. So you make another action by the help of those numbers or states, whatever, by the help of this info. And then you go through this cycle. At the end of the day, you try to maximize the return. So this is the sum of RT. So how do you act? What is the meaning of action? So let's dive into it. The policy pi specifies how the agent selects the actions based on the current state, which means that at any state, you choose an action. And this action is denoted by AT, and the action is actually a distribution. So this is given by a policy. The policy could be deterministic. In this case, AT, the action you choose, is a function of ST. So everything is deterministic. With probability 1, you choose this action. So it is not that interesting. So there is no exploration in this case, but it could be also stochastic, which is the interesting part. So AT is sampled from a distribution given the state. So you are at a state and you choose some action with respect to some probability distribution. So this is the meaning of sampling. And I have an example on the right-hand side. Let's say there is an agent and there are 4 options. So you can go right, left, and so on. So there are 4 actions at a particular state ST. So this is the given notation for the ones. So let me show in this part. So ST given means this is a conditional distribution. ST is fixed and you make an action with respect to this given info. So for instance, on the right-hand side, the agent selects A1, the action number 1 with 0.4 probability, and the rest that are written here. So the stochastic policy favors A1, but in a stochastic way. So it's not going to choose it for sure. So there is also some stochasticity here. So this is the idea. You still favor it, but it's a probabilistic thing. And I will give the definition of a trajectory. So the agent acts, receives a reward, and lands into a state. So if you continue in the cycle, there will be a trajectory generated. So we start with S0, take the action A0, go to S1, and then A1. So this is going to be a trajectory. S represents the state, A is the action. So over time, you have the trajectory tau. Sometimes these trajectories are known as episodes or rollouts in the literature. And you see another picture, another diagram. So S0 is distributed by mu. So this is coming from a distribution. It's sampled from some distribution, let's say. So we start at S0 and take an action A0, land it to S1, and then you go to A1, you take the action A1, and so on. So deterministic means if you are at state S1, you know that you will for sure go to some other state, which is known already. But if it is stochastic, you can land on some other states. So this is the meaning of being stochastic. So there is a distribution here. So this is the transition distribution. And what about the other notation? So I'm still giving the terminology. So what's a reward function? So we will use them a lot. So reward is the numerical expression you get after taking an action at state st. So you receive a reward or you get punished. If you get punished, for example, you can get a negative number here. But if it is something successful, if the action is successful in the terminology, you get something positive. And the important thing is this, of course, we have a trajectory. At each step, you gain some number r, and we need to take the sum of these because we are interested in the sum of the rewards. And if we have a finite horizon trajectory, it means the process stops at some point t, time t, then RT is going to be defined as the simple sum of rewards. But the interesting case is the infinite horizon case, because in the large language models, if the model do not stop writing down some sentences, it's going to be infinitely long. So this is something you don't want, for example. And RT is going to be defined as the infinite sum, of course, as expected, of RT, but this time we put a discounted factor here, discount factor. So I try to explain it on the right-hand side. As you see, gamma to the 0 is just 1. And if you take powers of gamma, and it's a number between 0 and 1, so this height is getting smaller and smaller. So if you take powers of gamma, you will get here a smaller effect. So it means that the reward you get in the next step is much more valuable than the reward you will get in the future. So you don't know actually either you will get it in the future. So this is also another discussion. But the reward you get now is much more valuable than the reward you will get in the future. So this is how you can understand it. So all in all, by the way, there is also a mathematical description here. We want this reward to be positive. Reward means here R. So R of the trajectory, we want it to be something finite. And from a mathematical perspective, this is going to be like if RT is bounded, it's going to be the geometric sum. So it's going to be finite for sure. And what is the RL problem that we are interested in? So for stochastic transition and policies, the probability of a trajectory means we start at some S0, we go to the next state, given S0. So you go to S1 by the help of the policy, by the help of the action A1, and so on and so forth. So you visit all the states labeled as S0, S1, and so on. So how it works is it's not hard. So I will denote this probability of the trajectory under the policy pi as this. So pi is given, so it's a notation, by the way. Sometimes it makes no sense because I use the same notation for different, say, quantities. So let's use this one. Pi is given. It's pi, the policy that we follow. All the trajectory is given by the distribution of the first state. And then if we know this S0, we will take the action. So this action is distributed by pi. And then there is a transition probability as we talked about it. So you go to the next state by using another probability distribution and you continue this loop. So if you go to S2, you will take the action A2, you go to S3. So you multiply all these probabilities and you are not 100% sure that you will take the action, so you sample it from the policy. So you multiply all these, that's it. So you multiply all the probabilities you see around, and this is going to be the probability of having that trajectory on the distribution pi or under the policy pi. And this is a distribution, of course. So we are interested in the expected run. Of course, you can take here the sum, the infinite sum, but let's say we take the integral, it's the sum, of course. So what is the expected return? So expected return means we will multiply R with the distribution of this trajectory R. So it is nothing but P that we calculated over there. So this integral becomes, or the sum becomes, expectation of RT or R tau as tau is distributed by the policy pi. So we simply integrate P times R. So
Can I
what?
ask you a question? Sorry.
Yes,
Yes. For the probability of a trajectory. So when we say trajectory, we have both state and actions. It's not just the state, it's both state and actions, right?
yes,
Okay. So when I look at like this probability is actually comes from like Markovness,
exactly,
like
exactly.
right?
So yes, this is modeled
Condition.
by
Okay.
Markov decision. Yes, Markov
Okay.
decision process, and yes, it's a nice remark. And of course, so I think what you try to say is the memoryless property, right? I mean, if you're at state ST, you go to ST plus one without regarding the previous states, yes. So you forget about the rest. So everything is determined by the state ST. So
Yeah.
you don't consider ST minus one and so on, yes.
Yeah. Yeah.
So
Okay.
yes, this is modeled by Markov decision processes. And what is the point? So we try to compute the expected reward, but the goal of this reinforcement learning business is to find a policy. Policy means the action sequence you will apply is going to be the one that maximizes this J. So you try to maximize the expected return. So what is the policy pi, which gives you the maximum number? And it's not unique, of course, but you can take one of them in this case. So this is going to be pi star. So we try to maximize this J. So J is the expected reward. So we will use this function in the next calculations, but the idea is to find policy pi. So we try to get that. And I generated an example, of course, a toy example. So you see S0. So let's say we have a finite trajectory. We start at S0, you go to ST, and we have three trajectories, as you see. And one of them is optimal. The red one is the optimal. And let's say the first one is here. It is R tau 1. And the red one is R tau 2, and we have R tau 3 here. So at each step, you receive a reward of 2, 1, 0 in the first one. And in the second one, you get rewards 5, 4, 3. And in the last one, you get 0, minus 1. So it is punished here and so on. So if you calculate the discounted sum of rewards, it is maximized by the second one. So it is the optimal policy for us. So it is the policy which maximizes the return. So we forget about the suboptimal one, optimal one. So we got this one. So this is the policy we need to follow. So it is what we try to say here. Of course, this is not that simple. And to do so, there are some methods. So I will describe it because we will use it also somehow. It's the value function. Again, it is coming from Markov decision processes. Sorry, and it's a lot to this. There is a lot to discuss, but let us stick to the notations. And I will use V pi S. So it means that if we start at S0 and calculate the expected return, I will call it as V pi S. It means the value of the state. So if you're at S0 and follow a policy starting from S0, what is the expected return? So you calculate this and it gives you the value of the state. And if you find a maximizing policy, I will use star asterisk of this expression. So this is going to be V star. And here is the example or diagram. You go from S to ST plus 1, but you use pi. And you get the reward RT plus 1, RT plus 2, and so on. So V means the value of the state, which is the expected return you get starting from that state. And there is another notion, so-called the action value function. So this is denoted by Q. So it is more or less the same thing, but there is one exception. So we put S and A, which means, again, you start at the state as 0 and you calculate the expected return, but the difference is this: you take action A at first. So you started at 0, take action A, and then follow the policy pi. So there is one exception, as you see in the picture. So you are at S, and then you go to ST plus 1, ST plus 2, but you take the action A at first. So this is going to play a role, a crucial role in the calculations. And then the rest is the same. So I use the star, which maximizes this expectation. So the only difference is this: in the Q function, we take the action first. So this is going to be any action, of course. It's not in the say policy pi, and then you follow the policy pi. So this is going to be the Q function. It's the action value function, and they obey nice rules. So these are they satisfy some recurrence relation, which is called the Bellman optimality conditions or Bellman equation. And what about the value functions under a policy? So you can calculate this V using this, say, equation, which means instead of calculating the value at one step, you first go to the next step and then calculate the expected reward at each step you can go, and then add the reward you receive while you process to the next state. So it is like you make an action, you get the reward, and then you can go to some other states. Let's say this is going to be S prime, and then you calculate the value of each of these states, and you take their average, multiply by gamma. This is the discount factor, and you can do it for Q as well. So what is the relationship between V and Q? So of course they are related. So V turns out to be the average of the Q functions over A, which means at the state S, you can take some actions A, of course, so there are lots of actions you can take, but if you take the average of all these actions, you are not taking the average of the actions, but you are taking the average of the Q values after taking these actions. This is going to be V. So these are related to each other. And if there is an optimal policy pi star, then V star becomes the maximum Q star that we applied A. So you choose the action that maximizes Q. This is going to be V star. So it means that if you got the optimal policy, then we know which action to take. So you take the action which maximizes Q. So this is the relationship between these. I mean, this is not going to be the main part of the talk, but it's enough to remember V and Q. So I may explain in the future, maybe if needed. And there is a fundamental existence theorem. Again, I'm not going to use it, but do we have an optimal policy under some conditions? Yes. So this is a Markov decision process with bounded rewards and discount factor. So there is at least one optimal policy pi star. In this case, we can calculate V using this expression. So this is the Bellman optimality equation. And there is a characterization of this. If there exists a stationary optimal policy pi star, then V star will be V of pi star, and pi star will be the action that maximizes the Q value, and so on and so forth. Again, these are not the main parts of it, but I need to give all these I mean, if I introduce V values or Q values, I need to mention these because you can ask if there is an optimal policy always. Under some conditions, yes. And in general, we have it. So now,
Ask one more thing
yes,
for the previous one. Yeah, so for this optimal value function, the uniqueness, there are some conditions?
I think yes. I mean, we want
Yeah,
bounded
right.
rewards, yes, discount factor, and there is at
Okay.
least yes.
Because like we know like optimal policy is not unique, so that's why I'm thinking.
Fine. Yes, and you use here the contraction principle, so you got that. I mean,
Okay.
and
Okay.
so you apply again and again. So you have, because of this gamma, you get convergence. Yes.
Yeah. Thank you.
You're welcome. And the important part is this. let me remind you what V and Q are. Again, this was the theory, which was not the main part of it, but here is the important part. So you can forget about what I said in the previous two slides. But here is the thing. We defined the advantage function. So this is the core part of the talk. So it is defined to be the difference between the Q value and the V value. So what was that? We are at the state S and we calculate the total expected reward. This is the function V. What is Q? You take one action, you take the action A first, and then you follow the policy. So the difference is the first jump, right? I mean, you go from one state to the other using the action A. So how valuable is this action? This is what we measure here. And you may think of V as the total expected reward, but expectation is the average, if you like. So this is the average this is the average reward you get in the future. And after applying A, you receive some value Q, and you subtract V from Q. It means you measure how good is this action compared to the average. So you compare the value of this A. So this is called the advantage function. And it's going to be described by A pi as A. I will maybe use some other notations in the next slides, but if A is larger than A, it means you get something better than the average. If it is 0, of course, you are more or less the same with the policy. There is no advantage. And if it is less than 0, your action is it's worse than the average. It means the following. So let me explain one more time. You follow a policy. So if there is no disruption, you follow the path, right? But if you decide to make another action and then follow the same path, then there will be a change here. So what is the meaning of this change? What is the value of this change? You measure that. I mean, if you receive a higher value after making this action A, it means that you did something better than the policy pi. So this is what we try to say here. The action is the advantage is positive, means you did something better than the policy while applying the action A. Now, let's dive into the gradient methods. These are well-known methods, by the way. I mean, these are well-known but studied objects. So let me describe what we try to do. We try to find a policy pi which maximizes the expected return over trajectories, if you remember. So we try to maximize the performance objective J. So this was the expectation of the return of the trajectory. And we can't find it, of course. I mean, it's not like take the derivative, make it 0. It's not going to work. So we use the gradient descent algorithm. So we find the policy gradient, so-called. We take the gradient of J of theta, pi theta, to perform the gradient ascent. So maybe I should stop here for a while and tell what this means. So we try to find a policy, and policy means the sequence of actions. So to do so, we parameterize the policy by some parameters. You may think of this as a neural network. And this theta looks like a usual theta, but you may think of it as a vector, of course. So a vector with billions of parameters. This is what theta is. So in DeepSeek, for example, we have like 671 billion thousand and parameters, and in llama model, for example, for the meta, they have like more than 3K billion, I guess. So this is the number they have. So there are billions of parameters inside. And we take the gradient with respect to theta. It means you take the gradient with respect to each of these parameters and you update the parameter. So hopefully at the end of the day, using this gradient algorithm method, pi theta will converge to pi star. So this is the expectation. This is what we try to do here. So it is the usual policy gradient estimate. Again, I repeat, the goal of this method is to find pi star, the optimal policy, which maximizes J. So to find it, we apply the gradient algorithm. And to do so, we parameterize pi theta by some neural network, and we optimize the parameters of the neural network. So this is the case. So we take the gradient of J and evaluated at pi theta k and at theta k. So this is going to give you the next parameter. And hopefully, as I said, this difference is going to be smaller between theta k plus 1 and theta k. So the whole thing will converge to pi star. And this is called an on-policy method. It means that at each update, you use the data which is collected using the current version of the policy. So this is just, this is just some terminology again. So we are using pi k to generate a trajectory and use this data. So I will explain in detail, but what is the point? Again, we try to calculate this gradient. So what is the gradient of J? This is the goal. But let me remind you what J is. It was the integral of P times so I'm not going to repeat, but it's going to be P times R, the integral, right? It is the expected reward. So let us calculate first the trajectory probability and the gradients. So now this is just a calculation. I will use it in the next slide. So this is just a preparation because out of nowhere I calculate something, but it is the one that is used in the calculation of J, if you remember. So this is P of tau. What was the probability of a trajectory if we parameterize it by theta? So this is going to be pi theta times P, and you take the product of these. So you remember that. And then I will take the log of this. So because there is a finite product, if you take the logarithm of this, it's going to make our life simpler. And when I take the gradient with respect to theta, there are some terms coming from the model without theta, so they will disappear, as you see. For example, the first one, the log of rho 0, S0, so there is no theta in it, it's going to disappear. And the term in here, it's going to disappear. So it means that the gradient of the log probability will be just the sum of the gradient of the logs of the pi theta. So P of tau is the trajectory probability. It's related to the sum of the gradient of the log of the policy that we have, pi theta. Now, again, I will use this in this calculation because I am interested in the gradient of J, as you remember. So what is gradient of J? It is the gradient of the expectation of R of t, as you remember. Now, let me use the definition. So this was something I tried to say a minute ago. So it is the definition of the expectation we try to calculate, and I'm taking the gradient of this. It is the expectation definition. Now, under mild conditions, you can put the gradient inside. Now it's like an engineering way, so you can put it, of course, in mathematics you can't say this, so you need to prove all these things, but let's say Lebesgue dominated convergence, whatever, so you can put it inside, and we have the gradient of P that we calculated in the previous slide. So let us substitute it inside. It was a log derivative trick, so we calculated that, and as you see, now we have the gradient of the log times R multiplied by P. So we take the integral of something multiplied by P, which means the expectation, of course. So this is the probability of the trajectory, and the trajectory is, say, is distributed with respect to pi theta. So this is nothing but the expectation. So we get all in all, the gradient of our objective function equals to the expectation of the gradient of the log times R. So we return the expectation form here. So this is what we got. So the gradient of the objective turns out to be the expectation of this quantity. But what is the point? So we got something, yes. Is this valuable? Yes, because you can use Monte Carlo simulation here, right? Because you have an expectation and you try to take the expectation over some trajectories. So you can't have all the trajectories because this is expensive. So you may take bunch of trajectories, you may sample bunch of trajectories and take the average. And this average will converge to this expectation. So this is the idea here. This is the meaning of this policy gradient derivation. So we can sample trajectories and we can get the expectation using this formula. Okay, again, this is something we got, and it is called the reinforced algorithm, which was given by Williams in 1992. So it is called the vanilla policy gradient, and there are some other names in the literature, but all in all, the gradient of J is nothing but the expectation. Again, as I said, the idea is to sample trajectories and use their Monte Carlo returns. Monte Carlo return means you sample a trajectory and you use all the action state pairs in the trajectory to calculate all this stuff. And what is the gradient estimator then? So you sample some trajectories, say D, we have and many of them. So by the way, I forgot to put here the cardinality symbol. It is not 1 over D, but there should be a cardinality here. It's like 1 over N if you like. So we take the sum of these numbers, sum of these quantities. So instead of the gradient of J, I'm going to use this sum. And of course, if you look at the sum, we start from T is equal to 0 up to the point T. It means that you are using all the actions that were performed so far. So this is going to lead us a high variance because of the full return. Because if you are at some state S, you don't care about the rest, right? So you need to go further. So this is why it's not going to be a nice estimation, but it was good, of course, at first. But we realize that it's going to give us a high variance respect to the full return. So this is going to be something slow and unstable learning. Of course, you assign poor numbers as rewards. So we need to have some improvement. And I now give you a theorem or a lemma, so-called expected grad-log probability lemma. So there is an OpenAI spin-up blog. So this is something I use also. And there they use this name, expected grad-log probability lemma. So this is not the name in the literature, I guess, but they use it like this. So here is again another theorem which says if you take the gradient of the log expectation without any without any reward, let's say. So without any reward, there is no reward in here, as you see. It is the same formula, but without any reward, you get expectation 0. I will prove it, but it means that this is the formula you have here is an unbiased estimator. So the gradient cancels out. And without the reward, there is no learning signal. So this is what we derive here. And I try to put here a sketch. So these arrow thickness gives us the probability ratios. So if you take the sum of these arrows, you will get 0. So this is going to give you a net gradient 0. So the expectation of the log gradient is 0. So I'm going to use it. Again, it is not on its own something important, but here is a proof. We take the expectation of the quantity we try to prove. So it's kind of a lecture, but that's fine, I guess. So ST is, say, sampled from D pi theta. And so this is like the marginal distribution, if you like. And this is the expectation of 80 we calculate. And for any S, the inner expectation becomes this. And you take the gradient of that. The gradient of this quantity becomes the integral of pi. And the integral of pi is 1, so you get a 0. So all in all, the full expectation is going to be 0. So I will just use the result. That's why maybe I'm a little bit quick, because I would like to talk about some other important thing. But all in all, the gradient log is 0. So what about the reward to go policy gradient? As I said, you remember that this was the vanilla policy gradient. It was starting from T0 to T. And this includes irrelevant past rewards, as I said. So you calculate all the rewards that are in the history if you are at S10, for example, you don't want to calculate the reward you get at S9 and so on. So you'll need to go, you need to look ahead. So that's why they define reward to go version of this. It means just define R hat, and instead of T, you put T prime, and T prime starts from T all the way up to T. So you forget about the rest at each step. So you don't count the rewards you receive at each step. So you just forget about the rest at each step, and you go and you look ahead. So this is called the future rewards. And we will use the reward to go version of this. So all in all, we have this formula that I try to mention here. It is the reward to go version. So it is with low variance. And we proved the version of this without R to be 0. So now comes the main part about the variance reduction part, and I will talk about the baseline. So let's say instead of putting R, let's say we put here phi of t. So I will substitute phi of t by some other expressions. Now, since I know that the expectation of the gradient of the log is 0, I can multiply with any expression without including any theta term. So this is going to give me an expectation of 0. So we know it. So I can multiply with anything I like. If it doesn't include any theta, that's fine, perfect. So that's why I can also write down expectation of this gradient multiplied by some b, so-called the baseline. It's going to be also 0. So we can add this term here and subtract. That's fine. So instead of phi, it was r hat. It was reward to go. So instead of this, now I will substitute r hat minus b. So this is going to be our phi t. And it is reward to go minus a baseline. So it is a common choice to take the baseline to be v. This is the old friend. It was the value function, as you remember. So there is no theta in it. So let's define the b function as vt, and then you have reward to go minus b, and we have the advantage function. After some calculation, you will get that the advantage function will show up. So instead of phi t, I can put the advantage function here. So we discussed earlier. So again, this is not maybe directly following from what I wrote down here, but if you do some work, you will get the advantage function. It's going to follow. So all in all, again, I sum up all the time. We try to find the gradient of j, which is the expected reward over trajectories. So this turns out to be the expectation of this quantity. And in the quantity, we have a sum from 0 to t. And you put the gradient of the log of the policy multiplied by some function. And this function turns out to be the advantage function here, all in all. Okay, now I will go to large language models. So we talked about the policy gradient. Now it was maybe a little technical. Now we go to LLMs. So maybe you know a little about these, or a lot maybe. So what is an LLM? I'm not going to go deep into it, but these are transformer-based neural networks, if you like. So there are lots of parameters to be optimized, and they are pre-trained over massive text corpora. So they search the whole internet, and they are trained over these. I will give details in the next slide. And in general, they predict the next token auto-regressively. So nowadays there are different methods, but you may say they predict the next token. And here's an example. Again, I generated. So you put, for example, to the machine or the LLM, like what is the capital of, and then the LLM, using its transformer architecture and self-attention mechanism, understands the context and then generates the answer. France is Paris. So this is okay, I guess. Yes. So the capital of France is Paris. Yes, this works. So you are not just generating the next word, but you generate the whole sentence maybe. And the important thing is this: the next token is given by a probability distribution. So this model is not just determining the next token. It gives us a distribution of words, and the word with the high distribution, high probability, will be most probably be the answer. So that's why you get different answers if you try the same question, if you try to give the same question to the LLM. So because the LLM generates a distribution at the end of the day, so it's going to select one of these. And this is called the temperature. But let us also discuss about this training pipeline. It is going to play a role. That's why I'm doing it. So as a summary, there are 3 steps: the pre-training steps, and the fine-tuning step, and the reinforcement learning step, of course, nowadays. So what is the pre-training? This is the self-supervised next token prediction. Again, the model search the whole internet or the given data piece and then learns the statistical patterns. But of course, doing this, it's not going to generate you the next words in a reasonable way. So it is not just tuned yet. And then due to your task, you fine tune it. So what is the task, for example? It could be math, it could be coding, it could be literature, whatever. So you can fine tune it using a supervised adaptation. So there are lots of methods to do that. Different models do different things. So you fine tune the model. Now it's going to give you some reasonable answers. And the easy way to say is to have helpfulness, harmlessness, and so on. It's going to be given by the reinforcement learning part. And for example, DeepSeek here uses reinforcement learning for the coding process and the math part. So they use reinforcement learning here. So there are 3 steps: pre-training, fine-tuning, and reinforcement learning. And we are here. So we will use reinforcement learning, and I will try to describe this part to you. But the other part is supervised learning and pre-training. So these are also other objects. And what about the LLM as reinforcement learning? Again, there will be an overlap between reinforcement learning that I described so far and the LLMs. So let's try to go into it. So the LLM itself will be the policy. It's going to be a stochastic policy, of course, because it generates some distribution at the end. So in the RL framework, this is a policy. And I will use, so in the literature, they use pi LLM. It means you are given some ST and generate AT, and theta is the parameter we use so far. So we try to optimize this theta. But I'm going to use, in general, this version on the right-hand side because this looks much better for our purposes. So this is going to be the same thing. So we have pi parameterized by theta, and the given thing is x. X is going to be the prompt. So this is the given object. This is the input. And y smaller t means the output generated so far. And so this is the given data. So you are given, for example, a prompt. It generated so far 5 words, and YT will be the 6th one. So you are given 5 words, predict the 6th one. So this is the meaning of this symbol, and you will understand why I choose it. So what are the connections? So ST will be the current input context. So this is the prompt and the generated tokens so far. So this is your state, ST. And action means the next token. Policy is the LLM itself. So we try to parameterize the neural network, which is parameterized by theta. So when we parameterize theta, we get the whole LLM. And a reward will be the human preference, if you like, in this case. So it could be something different, of course, but reward is a little bit different than what we had before, because at each step you will be rewarded, of course. So when you make an action, there will be a punishment or a reward. So it is going to be given in this talk by human preferences, and the trajectory means the complete generated sequence. So let's go to the advanced policy optimization method. So we had so far some theorems and the notion of LLM, and I will start with something important, so-called importance sampling. So what is the discussion? We try to estimate the expected return of a policy pi theta, and you remember we said that, okay, we got an expectation, and the expectation could be used using Monte Carlo simulations. So we can't generate all trajectories, but it's enough to take some bunch of the trajectories and take the average of these at each step. So we need to make use of it. And this is done by so-called importance sampling. So we try to get the expected reward that is given here, as you see. So this is J theta. We try to calculate this expectation. Okay, but the direct evaluation is not possible, of course, because we only have trajectory sampled from the known policy. So we start with a policy, we try to update it, but at each step, when you update, all the parameters change, all the action set changes, and so on. So this is not possible. We try to optimize pi theta, but we have data from pi theta k. So this is the bottleneck here. And the idea is, so how to overcome this problem? The importance sampling, which means basically you divide and multiply by pi of tau theta k. So you understand what it means. It is the probability coming from the distribution pi theta k. So this is just a trick. You multiply and divide by p. So you got this expression. It means that instead of having the expectation over pi theta, which is something we try to optimize, I can use the old policy. So old policy means the policy I have at hand. So you can generate trajectories, because to generate a trajectory, you need a policy. So this is the policy we have right now. So this is the trick, and we use this trick to calculate the gradient. So let us do it. So for a trajectory, let us calculate this ratio. So what is the ratio of P? By the way, I used capital P now. I passed to the lowercase p, I guess. So this is a mistake, but you can think of as capital P, that's fine. So you just write down these formulas, the huge products, and some terms cancel out, and this is what you get. So instead of writing this ratio over P, we can use the ratio of pi theta over pi theta k, and you take the product. So now I will substitute this into this expectation. And as you see, this was hard to calculate at first because we have the product of all the terms, but now it turns out to be just the product of pi theta and pi theta k. So we will optimize this function, but it is used in the literature or in the LLM literature as a surrogate loss. So we are not directly calculating this gradient of J, but another function L, say, is introduced. This is called a surrogate loss, so that the gradient of this function is equal to the gradient of J. So this is what is done in the literature. So instead of calculating this gradient, we will calculate the gradient of L. So they are going to be the same thing. So why do we do that? Because this J is not going to be, this is not the function, how to say, this is not the loss in the sense of supervised learning. So that's why we try to be careful about it. So unlike the supervised learning, the data distribution changes when you change the parameter. So everything changes. So it's not like something we try to optimize as we do in supervised learning. So this is a little bit tricky. And this is not a performance matrix. So it doesn't make any sense. The expected reward, the surrogate loss doesn't measure or approximate the expected reward. So this is just a function whose gradient is the same as J. So this is a function that is introduced. So I will introduce such a function, and the gradients will match, and we try to find the policy pi parameterized by theta, and that's going to be enough for us. So let's start with the first policy. Again, this is a huge thing. I will just go over that because we have better policies right now. So this is the first one, Trust Region Policy Optimization, TRPO, which is given by Schulman. So now, from now on, you will not see any J, but I will use L. So this was the surrogate loss. So what is the core idea here? We try to update our policies, but while updating the policy parameters, we need to ensure the updates to be not too large. So you need to restrict your steps. So this is the policy optimization method, which is introduced by Schulman at 2015. So what is this? We try to find the expectation. So you remember this ratio. It is coming from the importance sampling. And you have here a hat. A hat is going to be the advantage estimation. So you may think of it as the advantage here. So you remember the formula. We had the sum here, and you take the product of the advantage and the ratio. Now, as I said, I'm now using the surrogate loss, so these two gradients will be the same. So forget about the sum. Let's take the gradient of this object. Now, all in all, you will have this objective all the time throughout the lecture. So this L, the surrogate loss, is the expectation of the ratio of the policies multiplied by the advantage. And the trajectories are coming from, of course, pi old. Now I will use pi old. It means that this is the policy we have, and we try to optimize this theta. So what is the advantage function? Again, it is not easy to calculate, but we are using this estimation. So it's going to be the Q function minus the V function. So if you don't like this notation, it's going to be A and S. So this is the same thing. But of course, while doing this, we try to keep the update not too large. So you see here the KL divergence. It's the Kullback-Leibler divergence. It means this is kind of a measurement of the difference between, or the distance between pi old and pi. So you measure the distance between two policies, and we want this to be not that large. So that's why this distance is, say, restricted in a region bounded by, say, delta. And the mathematical formulation turns out to be this. So we try to maximize L, the surrogate loss, over theta, and the divergence is small. It means that you have the pi theta and pi theta old to be small. And now there are some technical details. I will skip these, but in here, you try to linearize the objective. And don't forget, theta is a vector. It has billions of parameters right now. And you need to have, you have a quadratic approximation for KL in this business, and F is called the Fisher information matrix. Again, this is huge. You calculate the Hessian here. And the natural gradient solution is given by a concrete formula. That's fine. But what are the computational bottlenecks? So there is the Fisher information matrix. Again, this measures the difference between the policies, basically, but it is a matrix with billions of rows and billions of columns. So this is expensive to compute. And at some point, you try to compute the inverse of it. It is intractable for large models. And you iteratively compute this conjugate gradient, but it is costly, of course. So it is a hard object. It could be done, but for large language models, this is hard to compute and it's intractable. So this TRPO means you have an objective in a bounded region. So you try to restrict the, say, update of the policy in a region. So there comes the PPO, which is the ChatGPT policy optimization at first. So now we have the clipped surrogate objective. So we have JPPO, we have X coming from a distribution. So this is, say, the prompt coming from a trajectory, and the, say, outputs are, they selected or sampled from pi all. Now, what do we do here? Again, we try to restrict the update of the policies in some bound, in some region. And this PPO offers a method which says, okay, so this is the importance ratio here. So you remember this ratio. We multiply this ratio by A, and we again multiply this ratio by A, but this time you restrict it between 1 minus epsilon and 1 plus epsilon. It means if AT, for example, is positive, and if this ratio, of course, is positive, then you may have a number very large, for example. So it says, okay, don't do it, just stop at some point. For example, let me give this easy example. You are a student, for example, you get 60, you get 60 on average throughout the semester. And for example, you studied a lot, you didn't sleep, and you get 90. So sleeping overnight is not good, for example. So, and you can, for example, get at least 80. So 90 is too much for you. So you shouldn't sleep. I mean, you should sleep at some point and you shouldn't follow this policy. So this policy is not good and so on. Or maybe a better example for LLM. So forget about the student example. So let me say like this. For example, you ask a question to the LLM, it gives you an answer which is so funny and you like it. So this is going to give you a high advantage. So you don't want it. You need to clip at some point. So this is maybe a better example. So this is the clipping. It means you keep the ratio bounded in a region. So this is the part, and it means that you surpass this KL divergence, the Fisher information matrix part, and continue. And here is the part, the main part here. In here is the update. You update the parameters. By the way, let me go back. So we calculate this, and you need to calculate A. And the advantage is calculated using the value function. So there is a neural network which computes the parameters of the policy. Fine. And while doing this, we need to calculate the advantage. To calculate the advantage, there is a value function to be predicted. It means there is another neural network that works in the background. So you need to calculate, or you need to have two neural networks in the system. One calculates the policy update, one has the value update. So using this and the advantage estimation, which is described here. So as you see, this is called the TD learning, by the way. I'm not going to, again, discuss all these. But while calculating the advantage, we use the value estimation. And to do so, there is another neural network, which is also as large as the policy we have. So the policy has billions of parameters. Now this value function has also billions of parameters. So you have an expensive model, but this works. And then we come to the group relative policy optimization, GRPO. So I try to mention the main parts, and in the GRPO, which is given by DeepSeek in 2024, last year, as you see, you have more or less the same representation. This time I multiply W by I. This was the same thing I multiply, so it is the ratio. This W is the ratio. Let me show you this. W is the ratio. You multiply by A, the advantage, and there is the clipping business again. So you don't want to take the advantage too much. So you just clip. If the answer is so good, you still clip it. And there is a summation I will explain. At the end, they subtract this KL. I will come to this moment. But what is the point, or what is the core part here? In here, the WI terms are the same. It is pi theta over pi theta old. So this is the policy to be updated divided by the policy old. And what is the difference between GRPO and PPO? Here, the advantage is not calculating using a value estimation. So there is no neural network here for this because this was expensive, right? I mean, you try to update the parameters of the policy. It was a huge neural network. At the same time, you don't want a value network. So this is not here. So instead of calculating the value function, they offer something nice. So they normalize the reward. It means they subtract the mean from the reward and divide by the standard deviation. For example, the LLM, the DeepSeek model, generates an answer, generates 50 answers, 50 outputs. Some outputs are nice, some outputs are bad. So they take the average of these rewards. So they assign some rewards for all these answers, for all these outputs. And they take the average of the rewards and compare with one of the individual reward. If the individual answer is better than the mean, then the advantage will be positive. If not, it's going to be a bad answer. So if the answer is worse than the average, it means a negative advantage. So this is the idea here. So instead of using the huge value network, they chose this way, which worked well. But I will explain one thing here. What is bad about this advantage? Because there are lots of critics about it. For example, the bad point is this, or the disadvantage of using this advantage method is this. If all the answers generated are correct, then the mean will be, for example, you get 1 point for each of the rewards. If you generate 50 answers, the average will be 50, and each reward will be 1. So 1 minus 1 will be 0. It means if you even generate a correct answer, you may get a 0 advantage. So if all the rewards are correct, so if all the answers are correct, then you will get a 0 reward, for example. So 0 advantage, sorry. So this is not nice about the group relative policy optimization, and people or some other groups introduced some other methods which improved this estimation, like DRPO and so on. So there are some other updates, but I'm not going to talk about it. And there is the KL divergence part here. So while updating the policy with respect to the current policy, they also measure the difference between the reference policy. It means this was the fine-tuned reference. So they control the update from two different, say, policies. They first control the policy using the current policy and the reference policy. So in here, this is the KL divergence. It is actually the log probability. This is the log expectation, but they don't use it. They use an estimation like pi ref divided by pi theta. So this is also given by Schulman in his blog. So you may check out this. If you write it down, you may find the answer. So all in all, the core idea is the advantage estimation. Instead of the value network, they use this normalization, and there is a KL divergence part here. So there are some critics about the method. I will not discuss it, but the main critic is given by the Quen team. So this is also important, and this is the one that was given like 2 weeks ago by the Quen team. So what is a group sequence policy optimization? This word is now different. So you see the same objective without the KL divergence. So they dropped it. But this time, instead of writing WIT, I will put SI. So what is this? The advantage is the same here. So again, there is a clipping. But instead of having the usual ratio between pi theta and pi theta old, they take here the geometric average, right? So this is the average geometric. And it could be proven that it is nothing but the expectation of 1 over yi and log of this probability ratio. So why do they use this? Because here is the idea. If you use just WIT, it means you clip the policy after one generated token, and you clip the policy, or you do the clipping one after the other. It means you generate one token and do the clipping, you generate another, do the clipping. They say, okay, the Quen team says, okay, you are missing the point, DeepSeek, they said. because this ratio is coming from the importance sampling. And importance sampling was nothing but the Monte Carlo method, right? So you generate a sequence of tokens and then you take the average. If you do it one after the other token, this is not going to work. And they proved it. They had some numerical examples for this. So they had some experience and they said, okay, this is now the correction. Instead of taking one token clipping, they use the sequence-based clipping. So they have the full token sequence and then they do the clipping. So it is given by this ratio. And this works well. So we discussed importance sampling. Now you understand how we use it. So this is a real life example for importance sampling. So basically, this is nothing but the chain rule of probability. So you just write down the ratio. It is the probability of x, y, I means you multiply all the probabilities so far, and you take the 1 over yi through it. So you got this. So what is the connection? The last line is the important part. The connection is this. The quant team changed WIT by the product of all WITs, and you take the geometric average of these. So this is the sequence clipping. And it works well. Again, this is related to importance sampling. Now I will briefly say something about RLHF and DPO, and then I will finish the talk. So let us talk about the reward modeling. So how do we apply the reinforcement learning there? So the RLHF, which is popular, which is popularized by, again, the ChatGPT, is this: how to train a reward model. So you need to train a reward model, which was expensive, as you remember. But because for each trajectory, you need to assign a reward, which is not possible, right? But they choose a way which is following the Bradley-Terry model, which says the user is given two different answers, and you're asked to choose one of them. So which one is good? So by using this technique, you can say order all the given answers. So this is what this model does. Yi minus means the bad answer, yi plus means the preferred answer. So this is the symbol here. This greater kind of symbol means yi plus is preferred to yi minus. So if you do it over a lot of answers, you will get something reasonable. I think this works. This is reasonable. So to train the model, I use LBT, which is the Bradley-Terry model. So it is given by the sum of the log of the sigmoid of R theta xi yi plus minus I theta xi yi minus. So this is the logistic function, and I presented a chart for you, and I will show where this is coming from. But all in all, this is the objective function. And here is a picture. So this axis shows us the difference between R theta. So this is the preferred reward minus the not preferred one. So if you're on the right, it means that you have the answer which is preferred. If you're on the left, it is not preferred. So this is the sigmoid function. It looks like the arctangent function. And it assigns a probability. So this is a function which gives you values between 0 and 1. So this is the meaning of applying this function. So you got a number between 0 and 1, and if you have something close to 1, it means that this is strongly preferred. If it is close to 0, it is not strongly preferred, of course. And you train this. If sigmoid goes to 1, human prefers pairs y plus. So why do we have this objective? Again, I try to put all the things that gives us the formulation. So what is this ratio? The Bradley-Terry model says, okay, you have a reward, x and y plus. You divide by the sum of the exponentials. So you take exponential of this reward, divide by the exponential of the sum of the total rewards. So this is nothing but the sigmoid. If you do some computation, you will get that. And we try to find, or we try to maximize the probability of the observed data. So you try to maximize the product of the probabilities of the preferred over the non-preferred one. So we try to maximize this product, and we call it as theta star. So instead of maximizing it, we maximize the maximum. We maximize the log of this. So this is called the maximum likelihood estimation. So instead of maximizing the product, you take the log of this, as we did before, and you maximize it over theta. So this gives us the objective. So it is nothing but the sum of the log. So this is called the Bradley-Terry probability. And we use, or ChatGPT use this RLHF to get the reward model. And the last one, it was given by Rafailov, and I think this is the Stanford team. It is the direct policy optimization. Again, these are huge things. I just wave my hands, give you some formulas, but they are huge. So we don't need reinforcement learning this time. So they learn the policy directly. This is why it is called direct policy optimization. So let's say there is a reward function R, which satisfies the Bradley-Terry model. So you remember this formula from the previous slide. And they match the reward model by policy. So in this case, the optimal policy under this reward model has this form, they say. Okay, the optimal policy will be the expectation of beta, so this is the temperature parameter, of R divided by Z, which is the partition function. It means you take the sum of all these rewards. So this is going to give you the optimal policy. So from this preference method, you can compute the optimal policy. Again, this is a huge thing. So I think this doesn't work for very large models, but for small models, this works well. And this is much better than RLHF, I guess. So this is what is said in the literature. So you have a preference model. Again, let's sum up. Let's say you are using an LLM. It gave you two answers. You prefer one of them, and this is repeated many times. And now you have a list of these info. So from this, you can calculate the optimal policy. Again, this is huge. And here is the key. Inside, the reward difference can be written by this expression then, if you recalculate it. And then you try to maximize the log of the P function. So you just substitute these and you get the objective function, and DPO maximizes this likelihood. So again, as I said, this optimizes the policy. So you get the policy model instead of getting a reward. So you just get directed without any reinforcement learning. So again, the last part is maybe it was quick. Sorry for that. But the main part was the objectives. I think I gave you 4 different policy optimization algorithm, like the trust region policy optimization. So as you see, this was given in 2015 and then 2017. The first one could be the PhD thesis of Schulman, I guess. And then we come up to 2025, the Quantine. And we have some previous results, of course. And this is the end of my talk. So thank you for your patience. And thank you again.
Yeah, thanks a lot, Berkay. It was, I
Welcome.
guess, very good comprehensive summary on various stuff that's difficult to follow nowadays, as you said. Yeah.
Exactly, yes.